Okay, now for some examples, and let's start with a very famous sum. Okay, 1 plus 2 plus 3 plus up to plus 100. Okay, now up to 100 we might be able to add it up, and a teacher, interacting with the great Gauss, a giant of mathematics, was fed up with this guy. He was always, up to stuff. And so the teacher said, I'm going to occupy you, for a while. Please add up 1 to 100. The number is 1 to 100, and the teacher was on his way out thinking, he's occupied Gauss. Before the teacher got to the door, Gauss shouts out 50-50. Okay, so this is 50-50. Okay, and we may wonder, well, how the heck did Gauss get that so quickly? No doubt, Gauss computed a formula for this sum. Okay. Now, here's a heuristic derivation of the formula. This is probably something along the lines of what Gauss did. And it's really ingenious what Gauss did. So, and let's even make it more general. Why do we need to add up to 100? Let's add up to n. So let's bring algebra in. So we're interested in the sum s equals 1 plus 2 plus 3 plus up to plus n. Okay, so what Gauss might have done is he said, you know what? I know about math. You can add things in any order you want. So let me reverse. So s equals n plus n minus 1 plus n minus 2 plus all the way up to plus 1. So I reverse them. 1, 2, 3 up to n. Well, now let me add. So if I add, I got 2s here equals n plus 1. N minus 1 plus 2 is n plus 1. N minus 2 plus 3 is n plus 1. Look, they're all n plus 1. And this is also n plus 1. Okay, so I got a whole bunch of n plus 1s, which I need to add up. How many n plus 1s do I have? I have n of them. So this is n times n plus 1. And there, with some even simpler algebra, Gauss concludes that the sum s is equal to 1/2 n plus 1. Genius. Okay. Not only can he compute now the sum up to 100, he can compute for any n. Okay, but do we believe this argument? It's got a ... fill in the blanks. Okay. So we might believe the formula, but this argument we may suspect because, is that a proof? Okay, so let's prove it by induction. And now that's, with the principle of induction in our back pockets, that's golden. Okay, so let's prove, so let's first make a claim. P of n is the claim. Okay, so there's a claim involving n. Now this is a fairly sophisticated claim. It's the claim that the sum 1 plus 2 plus 3 plus 4 plus n is equal to 1/2 n plus 1. That's the claim. Okay, and we might think, are we allowed to use this ... Well, later on we'll see a formal notation for this. Sometimes, once you learn that notation, we don't need the ... We write this as the sum from I equals 1 to n of I. Okay, but for the moment, let's take this informal notation for the sum. Okay. So this is what Gauss claimed. Now let's prove it by induction. So proof by induction. Okay, now whenever you prove by induction, you first establish the base case. So first step, base case, P of 1. Is it true? Well, what is the claim in P of 1? It's the claim that 1 plus up to n equals 1. So that's just 1. 1 is equal to 1/2. So n equals 1 times 1 plus 1, which is 2. So that's 2 times 1 plus 1/2. That's 2 times 1/2. That's 1. So this is 1. Check. So P of 1 is true. Clearly P of 1 is true. Okay, now comes the tricky part. Now we have to prove that P of n implies P of n plus 1 for all n greater or equal to 1. This is setting up the infinite chain. Okay. So in any such induction step, because we're proving an implication, we get to assume P of n. Okay. And that's the claim that 1 plus 2 plus 3 plus up to plus n is equal to 1/2 n plus 1. And now comes the tricky part. We have to prove P of n plus 1. So we have to prove P of n plus 1. Okay, we have to show P of n plus 1. Now it's tricky because you need to figure out what is this claim, and you have to be careful in plugging n plus 1 into the claim. So this is the claim, 1 plus 2. See here, n appears here, n appears here, n appears here. And wherever n appears in the claim, we have to replace it with n plus 1. So this is the claim, 1 plus 2 plus 3 plus n plus n plus 1. So we have to go up to n plus 1. This n tells you where the sum goes up to. So the sum has to go up to n plus 1, and it's going to equal 1/2. Now, P of n says it's equal to 1/2 n plus 1. So P of n plus 1, we plug in n plus 1 here and n plus 1 here. So we get n plus 1 times n plus 1 plus 1. Okay. Well, if we wanted, we could simplify. This is 1/2 n plus 1 times n plus 2. Okay. But that's, we've done it right. We've gotten the claim P of n plus 1. Okay. Now, it's just a question of we get to assume this, and we must prove this. So what did we get to assume? We get to assume this. So we get to assume that, 1 plus 2 plus 3 up to n is equal to 1/2 n plus 1. So 1 plus 2 plus 3 plus 4 plus up to n is equal to 1/2 n plus 1. Now the nice thing about proving an implication is we know where we are going. We have to prove this, which is the claim, which is the claim P of n plus 1. We have to prove that P of n plus 1 is true. So we know where we're going. So we're interested in this sum, but with one more term added, which is n plus 1. So from here, we can conclude that 1 plus 2 plus 3 plus 4 plus n plus 1. So I've added n plus 1 to this side, and that's the key step. Okay, it's what's linking what I'm allowed to assume to where I'm going. Okay? And that's usually the hard part of an induction. So this plus n plus 1, well, if I add n plus 1 to this side, I had better add it to this side. So it has to equal 1/2 n plus 1 plus n plus 1. Okay? And now it turns out it's just baby algebra. Okay, so I can factor out n plus 1. So this is equal to 1/2 n plus 1, okay, times, okay, so I have 1/2 n plus 1. So I factored out 1/2 n plus 1. I get n plus, I get, plus 2. Because 1/2 n plus 1 times 2, the 2 cancels that half and gives me this n plus 1. Okay, but this is exactly 1/2 n plus 1, n plus 1 plus 1, which is what I wanted. Check. So we conclude, therefore, P of n plus 1 is true. Okay, and that's always where the direct proof has to end. Okay, you have to end by showing that what you were asked to show is true. Okay. And so by induction, P of n is true for all n greater equal to 1. End of proof. And what is P of n? It's the claim that the sum is equal to this formula. So there, we've used induction to prove a formula. Now